very interesting. And today also we have two sessions.
A magnetic field. So this is the macroscopic where you can have a charge currents and you can generate the magnetic field and you can decide how much current you flow in that coil so that your magnetic field you can tune. But what is the atomic scale? The atomic origin of magnetism is like you have electrons in a material, you have atoms, and in atoms there are valence electrons. These electrons are having both, they are having a spin and they move in a orbit. So these electrons, they have a orbital motion and they have a spin. So the contribution for the moment is both orbital motion of the electron and spin of the electron. And another a small effect one can find from spin of the nucleus. The nucleus spin is very small compared to the spin of electrons, and the orbital motion, of course, that magnetic moment is also very small. When there will be a spin, there will be orbital magnetic moment. But when there is, in fact, if a atom you consider and all these electrons are paired, you don't have any magnetic moment due to spin. But there is, and the orbital magnetic moment is also zero. So whenever there is a spin, there is a orbital magnetic moment. And the fundamental magnetic moment, which we expressed as Bohr magnet, and that is your EH by 4 pi Nc, that is 9.27 10 to minus 24 ampere meter square. This is the fundamental unit of a magnetic moment, that is mu b. So, but this is the intrinsic magnetic moment of a material. But there is another effect one can find in when you are applying a magnetic field. So this is without a field, you have a spin of the electron, orbital motion, but when you apply a magnetic field, there is a induced effect. And this induced effect is always present. Whatever may be the material, it may be any kind of material, but always you find this induced effect. So that induced effect is always present. Of course, that induced effect may be very small compared to your spin magnetic moment, but when there is no spin, that induced effect dominates over this intrinsic magnetic moment. On the basis of that, you have different kinds of magnetic material. So these are the important quantities generally we use in magnetism, like magnetic moment, which is a measure of strength of the magnet. Magnetic field for magnetic field strength, which is in fact you externally apply this magnetic field. And magnetization is another parameter generally everybody use when you talk about magnetism, that is magnetic moment per unit volume. That magnetic moment you never compare, because magnetization is for unit volume, so you feel to magnetize. So that is your magnetic anisotropy. On the basis of all these parameters which we discussed, that one can have different types of magnetic material is diamagnetic, paramagnetic, ferromagnetic, antiferromagnetic, and ferrimagnetic. So diamagnetism, in fact, it is a property in all the material you will find, this diamagnetism. That means whenever you are applying a magnetic field, this diamagnetism behavior is found when you have no spin or orbital magnetic moment. Okay, so when there is no spin and orbital magnetic moment, then when you apply a magnetic field, it opposes the spin magnetic moment. So that opposing behavior, that negative magnetic effect is your diamagnetism. So whenever you have a core cell structure, you have paired electrons in any either in a atom, or you talk about a noble gas, polyatomic gas, ionically bonded solid, or covalently bonded solid. All these core cell structure give zero magnetic moment, because if they have no spin or orbital moments oriented unpaired electrons, or whenever there is no unpaired electron, there is no orbital magnetic moment associated with it. So this is the property of a diamagnetism. But when you have when you apply a magnetic field, then the magnetization is opposing the magnetic field direction. They get a negative magnetization. This is your diamagnet when you measure the N. But what happens to when you apply a temperature, when you heat a diamagnetic material? So when you heat, because diamagnetic material has no intrinsic magnetic moment, so it doesn't affect with the heating. So with temperature, if you measure the susceptibility and magnetization, it doesn't affect at all with the temperature. What happens to paramagnetism? The spins and orbital magnetic moment is there. It has a finite magnetic moment without applying any field. So that means you have the material which have an unpaired electron that could behave like a paramagnetic material, but always it is not true. But you need a unpaired electron for paramagnetic material, and these unpaired electrons, when you are not applying any field, they are randomly oriented. So you get zero field. At zero field, the magnetization is zero. As you increase the field, it needs to have a situation like this when it is saturated. That means all the movements should saturate aligned towards a magnetic field direction. But it never happens in paramagnetic material, because in paramagnetism the thermal vibration doesn't allow all these spins orient towards a magnetic field direction. It needs very high field. Practically it is impossible to magnetize a paramagnetic material. So you never get a situation like this, in this saturation behavior in paramagnetic material, though rather it shows a linear increase in magnetization with increasing field, and that susceptibility, that is susceptibility is nothing but your n by h, is very small, of the order of 10 to the minus 5 to 10 to the minus 6. But it is positive. However, in diamagnetic material, it is negative. And one thing I forgot to tell, in diamagnetic material, that it is minus 10 to the minus 6 to 10 to the minus 5, very small but negative. And in fact, in the superconductors, which will have the perfect diamagnetism, in that case, susceptibility is minus 1. Exactly same, the magnetization, increase in magnetization is exactly equal to the magnetic field. And that gives a perfect diamagnetism in superconductor. In paramagnetic material, however, we only achieve up to this linear increase region, not the saturation region. And this susceptibility, in fact, with temperature, it decreases with increase in temperature, and that gives rise to QD loss. Then the another material which is which behaves like ferromagnetic. That ferromagnetism is nothing but all these moments are aligned towards a magnetic field direction at applying at very low magnetic field, but without applying any magnetic field, this material shows a spontaneous magnetization. What do you mean by spontaneous? And this spontaneous magnetization means that without applying any magnetic field, they should have a finite magnetic movement. But can you think about iron? If you take iron sheet or iron metal, does it behave like a permanent magnet? Iron, nickel, cobalt are ferromagnetic material, but if you take a iron piece, it doesn't behave like a permanent magnet. Though, then what is this spontaneous? Spontaneous tells that it should have a magnetic moment without applying any magnetic field, but iron doesn't behave like that. Why iron doesn't behave like that? Because iron is a ferromagnetic material, but unless you apply any magnetic field, iron doesn't behave like a permanent magnetic behavior. But this spontaneous magnetization, the characteristic feature which is applicable for ferromagnetic material, the spontaneous magnetization is nothing but in a domain. So this domain means the ferromagnetic material is divided into large number of small region, which is known as a domain, and in each domain they are spontaneously magnetized. And they magnetize, and there is a magnetic ordering in this ferromagnetic material. So this ferromagnetic material, one can see when H is equal to 0, this is the picture of a domain only. Sorry, well, this is the picture. Each spin is representing one domain. So all these domains are randomly oriented, like in paramagnetic material. Each atomic spin is randomly oriented. Here, each domain is randomly oriented. Each spin is representing here a domain, and all these domains are randomly oriented. So at h equal to 0, you get a behavior like h equal to 0, m equal to 0. Okay, as you increase the field, then these domains, they align towards a magnetic field direction, and at a high field, at a field which makes them all align towards a magnetic field direction, all the domains become a single domain. So here one can see all these moments are aligned towards a magnetic field direction, and that is the case you get a saturation value in ferromagnetic material. And when you reduce the field, then again it doesn't come back to the same path, and rather it gives a remnant magnetization. And to remove this magnetization, you apply a negative applied field, and you get this Hc coincidentally. So this Hc and Mr, this Mr is representation of this ferromagnetic material. But without applying any field, you don't get this Mr. Okay. So this is the case of a ferromagnetic material. And you can see this ferromagnetic material, for example, iron, cobalt, nickel, a typical example. And all these get saturated, but one can see this behavior of the nature of saturation. The curve which is showing over here in nickel, cobalt, and iron is very different. In case of iron, it's saturated at very low field. However, in cobalt, it needs very high field, and nickel, of course, it's intermediate. Why this is so? And the value of iron, cobalt, nickel is different. It depends upon what? It depends upon the unpaired electrons in iron. How many number of unpaired electrons, that gives rise to your saturation value. And iron is highest, so it is having a saturation magnetization is high, then cobalt and then nickel. But this nature of curve is very different, and that depends upon the structure of the material. Okay, what kind of structure? And as I told, there are different EG axes. So iron is having a large number of EG axes, so it shows faster saturation magnetization at a low field. They saturate rather than cobalt and nickel. So this concept of domain is given by Weiss, and they show that this molecular field which is acting in ferromagnetic material, it acts below and above Tc, but this field is very strong that could magnetize the substance to saturation, even in absence of an applied magnetic field. And that spontaneous magnetization is spontaneous magnetization in a domain. And that domain concept is given by only Weiss. And Weiss assumption told that in paramagnetic material, these atomic spins, they don't interact with each other. However, in ferromagnetic material, and we assume that there is an interaction, and that interaction gives rise to a molecular field, and that molecular field is in fact proportional to the magnetization. So this is the magnetization process, how one can get this hysteresis loop. For example, this is a typical figure where you can see m equal to 0. These are two, suppose ferromagnetic material is having two domains. One domain is in spin up and another is spin down. And when you apply a magnetic field in this direction, then the magnetization, which is nearly equal to this magnetic field direction, that domain is growth. Domain growth occurs at the expense of the other domain. So this is the growth of the one domain at the expense of the other one. This is at low field. When you apply more field in intermediate field, what will happen? This magnetization, all these, the whole, both the domains now align towards a magnetic field direction, which is in along EG crystallographic axis. And this is along EG crystallographic axis, which is nearly equal to the magnetic field direction. And that higher field, the complete rotation of this magnetization direction occurs and it aligned towards a magnetic field direction. So at low field, domain wall bowing occurs. That means it is a reversible process. If you just reverse the magnetic field at a low field, you apply a magnetic field and measure the magnetization, and if you reverse, then you will get the same path, exactly the same path. It is a reversible process. But at intermediate fields, when the domain complete there is no two domains, it becomes a single domain, and then this domain translation occurs. It is not reversible, it is a irreversible process. And the high field, domain wall rotation occurs, and that is also a irreversible process. So here one can see this the same thing over here, that this is the low field from O to A to B. If you will reduce the field from B to O, then it is a reversible process. Okay, as you increase the field and it B to C, if you come back from C to B, then it doesn't come back in the same path. Rather, it takes another path, and that gives a minor loop. That is called a minor loop. And when you increase the field and it goes from C to D, it is domain rotation, and that doesn't come back again in the same path. So only there is a reversible process, but both domain wall translation and rotation are reversible process. And this, when you reduce, as we discussed, that again it come back to this is like when you reduce the field, then it come back to the another magnetic moment, which is not exactly why it is shows a remnant magnetization, because the domains are not exactly oriented the way it was oriented before applying a magnetic field. So that gives a remnant magnetization. So this is the domain. When you make large number of domains, there is energy associated with this, and that energy is known as magnetostatic energy. If you have only one domain, then most of the flux lines are outside this material, and that gives like a large field. So it is having a large magnetostatic energy. To reduce this magnetostatic energy, one can have large number of domains. If you make two domains, then some of this field is outside, and that gives a little lesser than over here. But if you make a large number of domains and all the domains are inside this material, I mean the flux are not outside this material, then it gives rise to zero magnetostatic energy. So this, when you make domains, then there will be a domain wall. This line is representing a one, so that one can distinguish between two domains. And that domain wall is 180-degree domain wall. Here one can see this, all these four domains are of domain wall, 90-degree domain wall. So you make these domains, large number of domains, to reduce the magnetostatic energy. So when you make a domain, two domains and separated by a domain wall, there is also a energy associated with this domain wall. So you cannot make having a very sharp line between two domains, or you cannot have a very large separation between these two domains. There is a competition between what kind of energy when you have this, all these things are aligned in one direction, then the exchange energy is very less. Here exchange energy is less, but as you and these exchange energy and the magnetocrystal and anisotropy energy is also less, because they are aligned along a crystallographic axis. When you change this orientation to have a magnet domain wall, then you change very slightly, because so that its exchange energy will be minimum, and but in this case, the magnetocrystalline anisotropy energy is now large, because these spins direction are not along the crystallographic axis. So there is a competition between exchange energy and the magnetocrystalline anisotropy energy, and that decides what will be its width. So there is a finite width depending upon this competition of both these energies. So in Curie law is mostly for paramagnetic range, when a material transform from one magnetic ordering phase to ordering state to a paramagnetic state, and that is in fact it is Curie law is C by T, but Curie law is again modified by Weiss, and that is known as Curie-Weiss law, because this molecular field HM, which is which arises because of the interaction between these electrons, that gives a fictitious internal field HM, and that is proportional to your magnetization, and that internal field in fact acted on the material in addition to the applied field, and that modify your Curie law C by T to C by T minus theta, and theta is the Curie-Weiss temperature, and theta decides whether it is a ferromagnetic material or antiferromagnetic material. So this theta in fact decides the strength of the interaction, that is depending upon the Curie constant. Curie constant is, gives the magnetic moment of the material. From Curie constant one can find out what will be the magnitude of this moment, and theta gives the strength of the interaction. So when ferromagnetic material is heated, then you will find that there is a transition from ferromagnetic to above a temperature, which is paramagnetic. That is the transition temperature is known as Curie temperature, TC. Okay, so this above Curie temperature, there is like paramagnetic material. So ferromagnetic material can be a paramagnet, or in fact, a perfect you may have a only paramagnetic material. So always you have to mention at what temperature it is ferro or para, because ferromagnetic material can be also behave like paramagnetic material. So this ferromagnetism, one can see that this slope is very small. It reduces very small with temperature. Up to zero point 0.5 of Tc, it almost the slope is almost the same. And above that, it decreases significantly and almost to zero. It is not exactly zero. You will never get magnetization at zero at Tc. Rather, it is very small. That's why this above Tc one measure the susceptibility. So that susceptibility behavior from that behavior paramagnetic range, one can find out whether it is paramagnetic or not. So this, if you have, as I told, there is exchange energy associated with these magnetic spins. If you have two spin Si and Sj, this Jex is the exchange integral, and that exchange energy is different for different material, and that decides the though magnetic moment is decided by the unpaired electrons, the Tc, the Curie temperature, is decided by the exchange energy. And if Jex is positive, in fact, always you need a negative energy for a stable state. If it is phi is equal to 0, that means all the spins are aligned in one direction, then this will be cos phi is equal to -1, so it is positive, and Jex has, sorry, something I did wrong. Anyway, this Jex has to be positive for when both these moments are parallel, when it is ferromagnetic. But when it is negative, then it becomes antiferromagnetic. Okay. This phi is equal to 180 when it is antiferromagnetic, cos phi is equal to so that okay, it's -1. So Jex has to be negative to have a negative energy, exchange energy. So here one can see this methacelator curve where this nickel, cobalt, iron is having positive exchange energy, and manganese, chromium will have negative. So in iron, cobalt, nickel, when iron is having higher magnetic moment, saturation magnetization is higher, cobalt is lower, but Tc is higher in cobalt because of this high exchange integral. Another class of material is antiferromagnetism, where you have M is equal to 0 means what? When you are applying, when you are not applying any magnetic field, you can think of in antiferromagnetic material, if you have two sublattice, then one sublattice is both the sublattice are ferromagnetically ordered. One sublattice is the other sublattice. Both of them are antiparallel. So both these sublattice, if you talk about two sublattice in antiferromagnetic material, both the sublattice are ferromagnetic, but the interaction between two is antiferromagnetic, and that gives rise to zero magnetic moment when you are not applying any magnetic field. But when you are applying a magnetic field, then some of the magnetic moment which are near to the magnetic field direction, that align towards a magnetic field direction, and the magnet susceptibility increases. Above a critical field, which is known as nil temperature, then again it decreases and it behaves like a paramagnetic material. So ferromagnetic can be a paramagnetic material, antiferromagnetic also can be paramagnetic material above Tc or Tm. So that one has to find out if you measure the susceptibility. And if you plot susceptibility 1 by chi versus t, this 1 by chi versus t, then extrapolate this straight line, you will get a negative value, and that negative value is minus theta, and that gives rise to your antiferromagnetic origin. That indicates it is antiferromagnetic. If here the straight line it cuts the temperature axis positive, theta is positive, then it becomes a ferromagnetic. Another class of material is ferromagnetic. In fact, if you, as I discussed, that in antiferromagnetic you have two sublattice. Here also, if you have two sublattice A and B, But in antiferromagnetic, both the sublattice have equal magnitude. But in ferromagnetic, both of them have not equal magnitude. So that's why they give a net magnetic moment. They behave similar to ferromagnetic material because they have a spontaneous magnetization, because both the sublattice magnetic moment is not equal, and they show a Curie temperature, hysteresis, all these characteristic feature of ferromagnetic material one can see in ferromagnetic material. So there are two groups of ferromagnetic material. One is cubic ferrite, cubic, and another is hexagonal. And this cubic is general formula is MoFe2O3, and this is called ferrites. M is a divalent metal ion, manganese nickel iron, cobalt, magnesium. Any divalent ion you can take and replace in M, that gives rise to ferrite. Similarly, cobalt ferrite. Among these, all these are all like manganese, nickel, iron. They are very small magnetic subferrites, and cobalt is in fact magnetically hard, and all other cubic ferrites are magnetically soft. And this Fe3O4 is in fact oldest magnetic material, which is known as lodestone, or called magnetite, and this is a ferrite. So this ferrites is having spinel structure. So this mixed metal oxides with chromium or iron oxide as main component, in fact it's a spinel compound. Large oxygen ions are packed in FCC arrangement, and in these spinel compounds it has 64 A sites, means A site is tetrahedral site, B site is octahedral site, 32 octahedral sites are there. So this out of 64 sites, 8 sites are occupied, and out of 32 sites, 16 sites are occupied. Its formula unit is Mb2O4. A is divalent cation, B can be trivalent cation. If A is divalent and B is trivalent, then it is known as normal spinel. If A is divalent cation occupying the octahedral site, and both this B2 is distributed among A and B sites, that is called inverse spinel. That means A site is B site is occupied, the divalent cation occupies the B site. In normal spinel, the divalent cation occupies the A site, and that gives rise to normal and inverse spinel. But in case of, if there is no strong preference for either divalent or trivalent cations, then it becomes mixed spinel. So this is the representation of tetrahedral and octahedral site, where divalent cation is surrounded by 4 oxygen. It is tetrahedral interstitial and octahedral interstitial, and this is a nomenclature of the cubic FCC lattice. So in ferromagnetic and ferromagnetic, the difference in with temperature is that in ferromagnetic material, as I told, up to 0.5 of Tc it remains same, but in ferromagnetic material, as soon as you increase the temperature, then this magnetization decreases very fast. Okay, so that and the Tc is also less than mostly ferromagnetic material. And another important parameter is that to distinguish ferro and ferromagnetic material is above Tc. 1 by pi is here it is non-linear. However, in ferromagnetic material we see that if you will have a straight line, you can extrapolate and find out whether it is ferro or antiferro. But here in ferromagnetic material, it is always shown non-linear behavior. So in this ferro and ferromagnetic material, the difference is, if you this is small and it is non-linear. If you talk about nickel ferrite, NiOFe2O3 is NiFe2O4. And that is, if you talk about nickel ferrite as ferromagnetic, then it should have 12 μb. But experimentally, it is observed that 2.3 μb is at absolute 0K, it has 2.3 μb. So that gives indicates that it is not ferromagnetic. Rather it is some different kind of magnetism, and that decided by the ferromagnetism. So if you have a ferromagnetic material and two sublattice, then both the sublattice doesn't behave similarly with temperature. This is A sublattice, this is B sublattice. If you increase in temperature, the behavior of A and B sublattice is different, and you get a net result is like this. Sometimes you may get a behavior like this, sometimes you may get a behavior like this. So that means what? You have a the magnetization decreases and it crosses the zero, and then again decreases and it gives a PC value. And this crossing of temperature at zero temperature at the temperature axis is known as compensation temperature. That means what? At this temperature, both the sublattice magnetization is exactly equal. So this is very important parameter, compensation temperature, where you observe mostly in ferrimagnetic material. So Niels' theory also explains this ferrimagnetism, this non-linear behavior, and that is not explained by Curie law, rather it is explained by 1 by chi equal to T by C plus 1 by chi 0 minus B by T minus theta. It's a hyperbola. If this equation is fitted with ferrimagnetic material, one can observe, one can find out the Curie constant C, and B and theta. B is a parameter which is a fitting parameter you have to find out, and it is associated with the strength of your interactions. So this is a clear picture for all magnetic material. 1 by chi, it is susceptibility. 1 by chi, where it is independent of temperature in dia. In paramagnet, it is crosses through zero because it is C by T. But if it is crossed through positive, then it is ferromagnetic here, and if it is crossed through negative, it is antiferromagnetic. Okay, and this is your above. This is non-linear. Is ferromagnetic. Okay, this is all about magnetism. Do you have any question so far, or I will finish? Then we will discuss. How much time I have now?
Another 20 minutes, 15 to 20 minutes you have.
Okay, okay, okay. So then
Okay,
I have to
students
go
will
fast.
ask question at the end.
Okay. So this is let us little bit just get the faster with nanostructure matter. Everybody know it as it is if it is less than 100 nanometer, it mostly called it as nanometer, but it is exactly not 100 nanometer. Is a very sharp part of calling it as nanometer. It depends upon the length scale of the material. Then nanomaterial have different properties. Why it is so? Because of this surface to volume ratio, and this one can see here. This bulk material will have large number of atoms which are inside the bulk, and the very few atoms are on the surface. However, if you reduce the size, it is almost exactly similar. The number of atoms are inside and outside. That gives you a surface area is higher, and you have a quantum size equal. So if you have 30 nanometer for typical difference, 5% atoms are on the surface. If it is 10 and 3 nanometer, almost 50% atoms are on the surface. And that the number of atoms are on the surface, why it is important? Because they are not completely saturated. The bonds are not saturated, and that is called dangling bonds. They have large number of dangling bonds, so they are very reactive than larger particles. So what happens if you reduce the size? Then you have a single domain, high coercivity, and you have a phenomena like superparamagnetism when you reduce the size. And the surface effects, in fact, lower coordination number, broken magnetic exchange bonds, surface strain disorder, these are almost affect the magnetization or saturation magnetization. However, this is affected your coercivity and of course saturation magnetization as well. So when you reduce the size, if you have a smaller bulk material, as you reduce the size, then you will have, sorry, you have a bulk material, and if you reduce the size, then you have two domains. You have finally you have a single domain. If you have a single domain, means all the spins are in one direction. So you have a very n spins, each of mu is mu, so total is, you will get a super spin of moment n mu when you reduce the size. And these are the energy which are associated. They are affected very much with the reducing the size. Like magnetocrystalline anisotropy energy is proportional to your volume. As you reduce the volume, it is in nanocrystalline range. If you increase the volume, this is increases. So magnetostatic, magnetoelastic anisotropy energy due to the effect of magnetostriction. And all this energy in fact is affected by reducing the size. So when you reduce the size, how this domain wall contribution is coming into picture. Here you one can see, if you reduce the size, this magnetostatic energy is proportional to your RQ radius, and the domain wall energy is proportional to R square. So as you reduce the size, the above, below a critical size, one can see here this domain wall energy is higher than the magnetostatic energy. So that means domain, if you make a two domains, then domain wall energy will be higher, then your state is not stable. So you need to have a only single domain. You cannot have two domains, because if you make two domain, then you have to have a wall energy, and domain wall energy is higher. So you have a critical size where you have a single domain. So in a particular critical value, in different material it is different. For a particular, below a particular value, it becomes single domain. In that single domain range, you can vary the size as well. And this size of this particles is in fact is proportional to your anisotropy energy K and inversely proportional to saturation magnetism. When you reduce the size, you can see from multi-domain it becomes single domain. As I talked about this single domain, in this single domain range, if you increase the size, your coercivity increases as well as your magnetocrystalline anisotropy increases. Below a critical size in single domain, you will have a size which is almost not, it is called superparamagnetic range. That means at below a critical size, it is even at a thermal energy Kt, it flips with a thermal energy. It doesn't have a stable state, and that is called your superparamagnetic range. So all superparamagnetic particles should have a single domain in nature. So if this superparamagnetic range, you will get a no hysteresis loop. This is a characteristic feature of superparamagnetic particle. It is saturated at very low field. It has a very high magnetic moment, but it doesn't show any hysteresis. So whole particle rotates like a single spin rotation as in paramagnets above a temperature called blocking temperature. So that blocking temperature, you can this depends upon the measuring time. The relaxation time of a superparamagnetic particle is depends on the measurement time period. If measurement time period is very fast or very small, that decides whether the superparamagnetic particles are relaxed or it is blocked. So it is different for different experimental measuring time. So first, above blocking temperature, the system must not show any hysteresis. That is a characteristic feature. And second characteristic feature of superparamagnetic material is that the magnetization curve must be temperature dependent to the extent that the curves taken at different temperature superimposed when being plotted against H5P. So if you take different temperature like 77 200, all this temperature H by P versus magnetization, it only superimposed on each other, and that gives you a behavior of superparamagnetic. So these are the magnetic measurement one can do to understand this magnetic behavior of the material. So this is nanofabrication. Everybody could have understood this. And these are the different types of techniques one use for nanoparticles. We have mostly used co-precipitation techniques, algal technique, precursor, spray drying I don't use, but hydrothermal. Hydrothermal is a very good technique where you can have a autoclave, and in that autoclave one can, inside this chamber you can vary this pressure gas, and you can vary the temperature as well. This temperature, this is the instrument where you can have different temperature up to 350. We can vary in hydrothermal autoclave. This is made in US for autoclave. In this autoclave, one can have different kind of morphology of the material, and agglomeration will be less. We have synthesized these TiO2 nanocrystals, nanofibers, and then nanoparticles, nanorods. All this I would just like to discuss about briefly about this material. This is iron oxide hydrothermally made. It is at pH 3, pH at different pH. One can see how the shape of the material is different. Not only shape, it is having a very drastic change in magnetic properties. One can see here generally coercivity is inversely proportional to size. Here the size is almost 6.5 micron, and this cubic set particle shows around 3000 to 6000 kilohs of coercivity. However, these are very small particles where one expects large coercivity, it shows around 600 or so. So this is the kind of kind of properties this material show. Iron oxide is very weak ferromagnetic, and it should not nobody could expect such high coercivity in this weak magnetic material. But we observe this kind of behavior in this pseudocubic particles of iron oxide prepared by hydrothermal. And this is the size, as I told, it is 650 nanometer, and we calculate that 3400 number of subparticles are inside this cubic set particles. However, in pH10, where it is 60 nanometer, it is almost single crystalline. So due to this large number of subparticles or crystallites inside a cubic set particles, that gives rise to such high coercivity. And this is the kind of coercivity we found of 3000 to 6000 Oxford, and that is decreases. This is the coercivity behavior with pH. Then one material TiO2 nanoparticles, we synthesize this TiO2 nanoparticles with hydrothermal method, and this TiO2 nanoparticles again used as a seed in autoclave, and then we could able to synthesize these bundles of nanofibers in TiO2 nanowires. Okay, and this when we dope cobalt, in fact the properties is very different. In TiO2, in fact a diamagnetic, we should not have expect any temperature dependent susceptibility. However, one can see it shows a paramagnetic kind of behavior, but it is not exactly paramagnetic. It is a contribution of both para and antiferromagnetic contribution, and that we calculated from this C versus T. We plot it 1 by pi versus temperature, so that it shows the antiferromagnetic because it cuts the temperature axis in negative. It is antiferromagnetic ordering, and extensively we understand why this x equal to 0 is having high magnetic moment than cobalt doping. That indicates from the oxygen vacancy, we calculate this oxidation state of titanium 4. Titanium is 4 plus or 3 plus, then whether it is cobalt cluster or oxygen vacancy, that decides the magnetic moment. Here one can see this titanium is corresponding to titanium 4 plus, cobalt is 2 plus. But when there is a and oxygen vacancy, in fact in pure TiO2 is higher than the cobalt TiO2, and that is because when cobalt substitution basically creates oxygen vacancy for charge neutrality, because in TiO2, the pure TiO2, there are large number of oxygen vacancy, and that oxygen vacancy is neutralized because of this cobalt substitution, and that reduces the magnetic moment. Next is MnO2. Recently, one student is working on this Mn manganese oxide. It has polymorphic phases, alpha, beta, gamma, delta, etc. And this different phase of manganese oxide, in fact, it is antiferromagnetic. And this manganese oxide is very important nowadays because of this energy storage, sensor, and catalyst. Doping of this zinc, copper, cobalt, iron enhances supercapacity performance. Cerium doping transform beta to alpha MnO2. So this kind of study we have done recently. This is the synthesis process through hydrothermal technique, and since taken manganese sulfate with potassium permanganate, and by changing this ratio of potassium permanganate with manganese sulfate, she could able to synthesize alpha MnO2, alpha beta, and beta MnO2. All these three is synthesized just by varying this concentration. And this is the XRD pattern of all these three phases. Intermediate phase, he has observed the gamma MnOH, which transformed to beta MnO2 after heating at 500 degrees centigrade. And this is alpha beta and alpha beta MnO2, all are all match well with this phase. And then from FKRC confirmed that it is MnO1, that 828 and 1371 is corresponding to MnO1. And same analysis shows two different types of nano fibers, that one is of 36 nanometer, another is 23 but this is of two, when it is a mixed phase, it is having two different size. One is 20, 30 and 115. So that also gives an indication of two different phases. Then XPS shows from XPS you could able to find out the Mn3 plus to Mn4 plus ratio is having 1.61 for alpha, beta it is less, and alpha beta is intermediate between these two alpha and beta plates. And accordingly oxygen vacancy is different. From this, sorry. Then magnetic measurement shows a nil transition at around 30K and in beta MnO2 and alpha beta is 20K. But however, when we measure this 1 by chi versus T, it shows the antiferromagnetic behavior, but this beta MnO2 doesn't show this antiferro, it is on the positive axis. And that could be due to this two sublattice model which I discussed, that both the sublattice are antiferromagnetic, but both the sublattice is antiferromagnetic, each sublattice is ferromagnetic. The inter-sublattice interaction is stronger than the intra-sublattice interaction is stronger than the inter-sublattice interaction. That means ferromagnetic interaction is dominates over here, so that we get a ferromagnetic like behavior, weak ferromagnetic, not very high strong ferromagnetic behavior, but it shows a ferromagnetic interaction over here. And from that, we calculated this mu effective magnetic moment, which is alpha for alpha is 5.12, beta 3.96, and alpha beta is 5.64. Taking this effective values, he has calculated the exact composition of MnO2. It is not exactly MnO2, rather it is MnO 1.48, beta MnO2 1.98, and alpha beta is 1.15. Substituted in this value in this equation, she could be able to find out exact composition of the MnO2. And then she did this image measurement, and at high temperature above this in paramagnetic range, it behaves like a paramagnetic, but in low temperature around 2 Kelvin, she calculated this coercivity, which is 4 kilowatts, so it's very high, and in beta it is very small, it's 0.6. And then because of this MSST, where we obtain a peak value, that that could be due to superparamagnetic behavior or spin class behavior. To understand that, we measure this susceptibility, and from susceptibility measurement, one can see that this is independent of the it doesn't change with frequency, the peak position. However, in beta MnO2, one could able to see this behavior is frequency dependent. And this kind of transition we didn't observe in N versus T. Rather, we observed this behavior in susceptibility ASIC. And this again is fitted with different law for Vogel feature and power law and Arrhenius law. And we could able to find out whether this behavior is spin class or non-interacting superparamagnetic or the cluster class. That is decided from this fitting of this susceptibility with frequency with different law. So then we did this as it shows like okay. So as it doesn't behave like nil
May
RNAs,
I
which
interrupt? Chandana madam, please
yeah,
conclude.
okay. So this is remnant magnetization. Just these two slides, okay. Remnant magnetization, we measure what is this remnant magnetization. We cool the sample with 100 Oersted field up to low temperature. Then we just remove the field and measure the magnetization up to 1400 seconds. Then we see that how the magnetization is decreases, and that magnetization decreasing value we fitted with this law, and then that is this like sorry, this okay. Then we stress exponential function, we confirm that these are the spin class behavior. So this is another delta MnO2, similar polymer of alpha, like alpha beta. This is another delta MnO2, and I am not discussing about this, just I am showing these slides. These are of all are nanofibers. So I am telling all these things because hydrothermal technique is such a technique one can change drastically its not only size, shape, and but also its physical properties. So this is temperature dependent magnetic behavior. Similarly, she has done these calculations, and then from HPS we could able to find out the oxygen vacancy, and from member STR different fields, we exactly find out the spin glass temperature by fitting with a AP line. And then field dependent shows how it is the MH curve is giving exchange bias phenomena or not. And then susceptibility behavior gives rise to its spin glass and cluster glass behavior. Okay, so this is all the similar feature we have. She has fitted with Paola logarithmic stress exponential function. It is well matched with the stress exponential function, and we confirm that this is a determinant to nanometers exhibit spin glass relaxation at low temperature contributed by interaction between Mn3 and Mn4 plus. Weak ferromagnetic below TF is due to magnetic frustration. Okay. So this is another alpha which is doped to dysprosium. I'm just giving this is explained through core cell structure and finally the conclusions. Thank you. Thank you.
Thank you, madam, for such a nice talk. You gave a uh, detailed insight of magnetism in different materials and especially in the magnetism and nanoscales. So there are few questions for you in the chat box. Now I am
Okay.
going to read out these for you. So kindly respond.
Oh, yeah, yeah.
So one question is by Shweta Das. What is the origin of molecular field below Tc in ferromagnetism?
Below Tc in ferromagnetism, molecular field arises because of the interaction. Okay. In
Okay.
Curie proposed that there is no interaction between atomic magnetic moments. They are all independent. However, in ferromagnetic, we proposed that there is a interaction. Without any interaction, if it is there is no interaction, you should not have a magnetic moment which is almost like I showed that Curie ferromagnetic material that susceptibility versus temperature. It shows up to 0.5 of Tc, it remains almost same. If there is no interaction between the magnetic moment, then immediately you could have get the paramagnetic. That magnetization should be zero immediately because spin-spin interaction there is very small interaction energy is very small. So always the origin of molecular field below Tc, or not below Tc, even above Tc also molecular field is there. It is always there. But only thing is that below Tc it is dominating, above Tc it is not dominating.
Okay, thank you, madam. So another question is on magnetization versus temperature slide which you showed. He has asked
In
what is the
zero field
significance?
cooling, yeah,
Zero
yeah.
field
What is
cooling.
the significance of a peak in zero field cooling curve?
Cooling. Yes.
Yeah, in zero field cooling, what do we generally do? We cool the sample with zero field, and then at low temperature again we apply a field and then measure. When you cool the sample and when you apply at low temperature the field, there is a competition between your field and the temperature. So field always tries to align the moment, and temperature always tries to disalign the moment. So when you apply a field at low temperature, this temperature effect is small. That's why the magnetic moment increases. Above a certain field, again it decreases because temperature dominates the field. Okay, that's why
Okay.
you get a peak.
Okay. So there is another question. I don't know whether it is suitable here or not. It's by Shaloni. So she has asked, what is the basic principle of thin film multiferroic materials?
Basic principle of thinking.
So I
But
do.
what
Okay.
context? Basic
Yes. Yes.
principle.
So
What
it's not clear
context?
here.
Uh-huh. Okay, okay.
So
A thin film material, if you will make means what? You are reducing a size, reducing one dimension. Okay. So even in different dimension, you can reduce the size. So if you have a thin film means you are you both length and breadth are like bulk. You are reducing the thickness. So in thickness you are confining, but in both length and breadth there is no confinement. So it is one dimension confinement only. Like you have in nanowire or nano rods, you have two dimension confinement. Only in length it is like behave like ball, but in radius, the whole area it is confined. So in thin film, principle of thin film multiphase material, I don't understand what you exactly want to ask. But thin film is basically different, much different than your bulk material in this context. Whatever material it may be multiferrite, it may be normal any ferroic material, it may be magnetic material, whatever may be the material, the properties will be very different if you have a bulk, you have a thin film.
Thank you, madam. So,
Sir,
since there are
sir,
no more,
sir, I have a question, madam.
Yeah.
What are the applications of super paramagnetic materials? Means where this magnetic behavior is used.
Super paramagnetic material very much useful in hyperthermia.
Achha.
Hyperthermia is like tumor treatment. Recently, one work we have done in this hyperthermia, the ferrite
What is that?
material like
What is that hyperthermia? Please explain.
hyperthermia is you are giving a temperature. This super paramagnetic material, when they will saturate, that will give rise to a heat, the heat energy, and that heat energy will kill the bacteria of tumor cells.
Medical applications.
Yeah, it is a useful medical application.
So let us thank the speaker for delivering this nice talk. It was very, very interesting, also useful for students. Students must have followed it very nicely
I have
because
given
madam
for
started with.
students that I cover most of the magnetism, the
Uh,
basic
so
magnetism. I didn't show much of my work because it may not be interest to them.
So
Only
you
the
started with very simple basic concepts and ended with some applications. So I feel it is very, very interesting for all participants. So thank you, madam, for your
oh, thank you
presentation.
very much. Nice to talk.
So,
Should I leave?
leave.
Okay, thank you, thank
Next
you.
speaker will
thank you.
continue. Thank you. Niharika,
So,
madam. Niharika, madam. Have you joined?
Hello, can you hear me?
I can hear you.
Good
So please,
afternoon, everybody.
and good afternoon. Welcome you, madam. So please make your front screen open to the first page and make your video on, then we'll start.
Yeah, is it
Yes,
visible
yes.
now?
Yes, visible. So please make your video on.
Video is already on.
Okay, okay. So
Yes, it is on.
this, okay, thank you. So this is the last session of today's webinar. That is the last session of the last
Okay.
day. I hope all the talks are very, very interesting for all participants, and you will enjoy the last talk also. So let me introduce Professor Niharika Mohapatra, professor at School of Basic Science, IIT Bhubaneswar. Professor Mohapatra did her MSc from Utkal University. Then she joined for PhD at IIT Bombay, and her research interests are experimental condensed matter physics, strongly correlated electron systems, including magnetically driven ferroelectrics, thermoelectric oxides, high temperature superconductors, low dimensional and frustrated magnetic systems, and magnetocaloric intermetallics. So, and also she has very good publications, more than 100 publications. She has published in different reputed journals. And today she will be talking about anomalous Hall effect, Berry curvature, and new electronic phases of matter. So with this note, I welcome Niharika madam to present her talk. Hearty welcome you, madam.
Thank you so much, Dr. Roja, and also thank you for inviting me to present a lecture on this webinar platform. So, 1 minute, my yeah. So, thank you
So
so
madam, your
much.
video is not on. Please make it on. Video we
Uh,
cannot see.
No, no, ma'am, video.
Video is on, madam. There
Okay,
are
okay, okay.
actually two windows. I have connected through two windows. So, in one window, it is on.
Okay, okay, okay. Please continue.
Yes.
Madam, excuse me, madam. Madam,
Yes,
keep
sure.
your PPT full screen, madam.
Sure, sure.
Thank you, madam.
Okay, so thank you so much for this invitation. And because there will be most of the students, the participants are mostly students. So I have prepared this talk basically for students. I have tried to keep it as simple as possible. And this will not include my research topic basically, but I tried to choose a topic which the students probably will, I hope they will be interested in. So I'll show you the connection between anomalous Hall effect, or the connection between Hall effect. Berry curvature is like a quantum mechanical phases, and how do we connect Hall effect with this Berry curvature, and then we can specify different types of electronic states out of this. So I'll show you a connection between all these three different kind of, I mean, which looks very different from each other. I have tried to keep the mathematics simple, but and though I have skipped many of the steps because there are long calculations involved. Um, okay, let me start. This will be the outline of my talk. I'll first introduce different types of Hall effect, then the connection with Berry curvature, and then I can show you the anomalous Hall effect without any net magnetization or magnetic field. Then how do we observe different types of phases? How do we connect this with different types of phases of matter? So, I mean, because of the title of this webinar, I just made this slide. If you choose any chunk of crystal, so if you take a crystal and try to zoom and see what is there inside, you will see that the atoms or ions are arranged in some sort of pattern, and they are arranged in a very symmetrical pattern, which we further can look at the electronic orbits, I mean, there are the orbits, then electron, I mean, clouds surrounding that, and all those things, and they are arranged in a specific symmetrical order. So the symmetry you can explain in different way. Then in real space, what you see, then in reciprocal space, you look at, or the momentum space, you look at the brilliant zone and all that you might have read in your standard solid state physics course. So basically, the symmetry is very important because the symmetry is linked with the band topology. I'll show you the link later on. So depending upon different types of symmetry, then your band structure totally changes. And let me come to the band. Like when you take a individual atom, you have discrete energy levels like this. And when you make a crystalline solid, you arrange them in different types of symmetry. So you will have some sort of, like, instead of discrete energy levels, you have bunch of energies or bundle of energies. The energy bundles or bunches, then you call the energy bands. Instead of simply energy levels, you call them energy bands. And then there the symmetry, and you might have read in your standard course that there are forbidden zones or forbidden energy zones, and which form the energy gap. So if you look at any real band structure, they are not as symmetrical as we saw in schematic view. So the realistic band structure is something so complicated, but we are not actually interested in looking at all the bands that are arranged or all the bands that are formed inside the solid. What we are interested is only those bands which are very close to the Fermi energy. Or in 3D case, you say the Fermi surface, like for all the well-defined Fermi surface. So I mean, what do we look at this Fermi surface or band topology when we are talking about the electronic transport? Because the title is Hall effect, then I'm showing you some bands. So there is a relation of this Hall effect or whatever the Hall conductivity that you get with this band structure. So basically, if you come to the solids, so in solids you typically divide the metals, or you categorize the metals into insulator metal, semiconductor, or semi-metal, depending upon this band gap. And this gap, you are looking at the gap near the Fermi energy. So at the Fermi energy, if there is no gap, there is overlapping of the levels, you say that to be metal. Then very minute overlapping or just touching of the bands you call semi-metal. Then when gap arises, then you call insulator. If the gap is small, you call semiconductor, because by thermal energy, by providing thermal energy, you can have some electronic states at the Fermi energy, and you can have conductivity. So this is the typical picture. Then if we look at the electronic states, basically inside the solids, you will have the electronic states. They are actually at the potential of the ions. Okay. So in the solid, you have the periodic potential, and in the periodic potential, so in the periodic potential, you have the electronic states. Okay. So basically, the electronic states are defined by the simple blocks wave. So then you calculate the dispersion relation and all that. So those things I will not elaborate. I will come to your simply transport. So this is particularly, I will not elaborate also this slide. This is a typical schematic behavior of in any kind of phase transition in solids. So some sort of phase transition, I mean any sort of phase transition that is always associated with some symmetry. So any spontaneous symmetry breaking is always linked with some sort of ordered phases. Okay, so I think Dr. Samal has already explained sort of phase transition on this ordering. Then like yours, this is always associated with some sort of order parameter. Okay, any discontinuity of the order parameter gives you a sort of symmetry breaking, like magnetization in paramagnetic to ferromagnetic transition, or density in solid to liquid transition, and so on. In superconductivity, you have the superconducting order parameter, and like that. So we'll not go into the detail of the symmetry breaking phenomenon, but what I would like to specify that you can also have phase transition without any order parameter, without any discontinuity of the order parameter, and that I will show you later on. So our interest is to look at the electronic transport through the solid. So each crystal as you know that it has a particular symmetry. So depending upon the crystal, so each crystal is behaving like a new vacuum with each crystal has its own electronic properties, and we need to understand this electronic property. So this is basically, I mean, what we are looking at. We are looking at the properties of the solids. Okay. So electronic transport. Now I'll come to the kind of type of transport. So basically, the transport, we are not looking at simple electrical transport, but your Hall transport. And this is the family of Hall effect that generally we see. Start normal or ordinary Hall effect, anomalous Hall effect, spin Hall effect, then quantum Hall effect, quantum anomalous Hall effect, quantum spin Hall effect. So this is the sequence of discovery from 1879 to 2013. So I'll give you a glimpse of all these Hall effects and what exactly, how they are different and in which material we observe this effect. So we'll start with your simple Hall effect, which you generally perform in your solid state physics laboratory. So this was first demonstrated by Edwin Hall in 1878. So in a gold foil. Basically, he took a two-dimensional metal sheet. In this sheet, if you apply magnetic field and electric field perpendicular to each other, so you will find a transverse voltage, like if you take the sheet in XY direction, be along the G direction, and if current is flowing in X direction, then you will have a voltage drop across the Y direction. And if you calculate the Hall resistance, you will find this to be linear with the magnetic field. This is the typical experiment that you perform in your course or in your laboratory. Now, if you little bit do the calculation, you find this to be minus of 1 by NE. So this is the typical experiment, and from that you calculate the carrier concentration and all that. So let us try to understand little bit this Hall conductivity. So your simple Ohm's law, from the simple Ohm's law you get J equals to sigma E. Sigma represents the conductivity. But this is I mean, if you have a very isotropic material, you just write sigma. But in general, for a two-dimensional sheet, this sigma conductivity is not a constant. It is actually a tensor in any material. So if the material is isotropic, you have sigma xx, then sigma xy and sigma xy are the off-diagonal term. This is the diagonal term and off-diagonal term. And to find out the expression for sigma, either xx or xy, you use simple Roots model. And by using Roots model and your Boltzmann transport, you can write this expression. I hope you must have done this. So in a steady state condition, when we say that the net in a steady state condition, there is no net current in that. So you will find that you can make this to be 0. So the left hand side could be 0. So by setting that, you get the expression of the conductivity as minus of NEV. So this is the typical conductivity that you calculate. Now, if I introduce in presence of a magnetic field, you can show that there will be cyclotron frequency. So the conductivity, I mean, you can calculate this from the resistivity one. So with the cyclotron frequency, which is known as EB by M, now introducing that, you will get your conductivity to be sigma naught by 1 plus sigma naught is the conductivity without any magnetic field, and then the sigma is given by this particular matrix. This is the conductivity. In this matrix form, if you write the conductivity and also the resistivity, you will find they satisfy the relation sigma equals to 1 by rho. The conductivity is inverse of the resistivity, and this relation is satisfied in matrix form. Remember this. So later on I will show you that in which case this relation is violated. That I will show you when we will discuss quantum Hall effect. Okay. So simply from this relation you can find out the Hall conductivity as minus of 1 by Ne. So this is simply you get this one and rho xx to be constant over here. The point to be noted is that rho xy is linear with B and rho xs is constant. Rho xx is dependent on the scattering time tau, whereas rho xy is independent of any of the extrinsic parameter. It is dependent on only B, the applied field, N and E is the charge, N is the effective carrier. Anyway, Drude's model is not it's based on your free electron model, which is not applicable to most of the real materials. So it fails at many instances, and this is one of the case where it fails because it for semiconductors, if your carriers are holes or electrons, this doesn't tell you a sign about the carriers. So later on, this was derived from the semi-classical level. So where we consider like your quantum mechanical thing, you have bands, you have energy levels like that. From the energy levels, again, you can get your velocity. So from that velocity, now you can get the relation, and from the relation, again, you can get the current carriage by each electron. That current is minus of EVN. N is the band, that energy band index. So you get this current. Now, once you get this current, if you integrate this current over the entire Brillouin zone, if you have a field band, this gives you 0 because the field bands don't carry any current. They don't contribute to the current. So you get this current to be 0. Now, suppose we have unfilled bands. So some of the levels are filled and some of the levels are empty. So what do we do for the entire one? If we take the total Brillouin zone, so we take the filled band as well as unfilled band, this will be 0. That implies that this addition of these two gives you 0. So the contribution of the filled band will be equal to the contribution of the unfilled band. So you can see that if you compare these two, one is negative, the other is positive. This actually gives you the concept of hole over here. From here only we get the concept of hole or positive carriers in the system. The anomalous Hall effect. So you can see this below the ferromagnetic transition, you can see the Hall resistance that varies as the magnetization of the material. So there are several mechanisms, some intrinsic mechanism and also extrinsic mechanism. So intrinsic mechanism was first given by Karplus and Luthinger, and that involves spin-orbit coupling, whereas the extrinsic mechanisms are subsequently proposed. So in this case, the necessary condition is that time reversal symmetry must be broken. So the system must have some magnetization. Okay. Now, the first one is spin-orbit coupling. They say that if there will be strong spin-orbit coupling, I will come to this Berry phase case later on. I'm just explaining if there will be a spin-orbit coupling, and then the electrons with different spin will deflect into different directions. So if upspin will move in upward direction, downspin will move in downward direction. Now, the other two mechanisms, the side jump scattering and skew scattering, you'll see that these two also give you the same result, although the initial condition is different. In both the cases, the initial condition is like some impurity or some antisymmetric spin orbit coupling that arises due to the transport electron. And in both cases, this creates some sort of potential gradient. So how do we understand this potential gradient? This potential gradient is the effective electric field. Basically, this is the effective electric field, and which the electrons see as a kind of magnetic field. And that can be understood if we look at the spin-orbit coupling effect. So basically, the spin-orbit coupling or the spin-orbit interaction is a relativistic effect, and you can understand this. Why I say relativistically? Because if we look from nucleus point of view or nucleus frame of reference, you will see that the electron is revolving around the nucleus and it's creating some sort of magnetic field. Now, if you sit on the electron, if you look from electron rest frame of reference, you will see that the nucleus is revolving around this electron, and that creates a magnetic field. So this effective magnetic field is E cross B by mc square, and this is the effective magnetic field that is experienced by the electron which is revolving around this nucleus. And then ultimately, this magnetic field will interact with the electron spin and give you this spin orbit Hamiltonian, which is expressed in terms of like E cross P dot sigma. This is the Pauli spin matrix that we are taking, and always you can connect this with the electron spin. So this is like for the free electron, and the same concept, the concept is like the spin-orbit coupling, but in crystal lattice there is a little difference. The difference is that the electric field that we are taking over here is actually originated by the potential gradient develops in the crystal lattice. So you must have heard of some sort of like crystalline electric field effect. So inside the crystal, because of the arrangement of ions and the charges, so there can be some crystal field. And in the case, let's suppose there is inversion symmetry breaking or something, so then you will have a net potential difference that develops within the crystal. And this potential difference, you can take it and attribute as a spin orbit field. And this field which interact, this potential difference and its momentum interacts with the spin of the electron, and ultimately it gives you a spin orbit field. And this electronic spin interact with the spin orbit field, give you the spin orbit interaction term or spin orbit coupling term. Now what we have to look at it is that the spin orbit field is odd in electron momentum. That means when you change the electron momentum, you will see that this is odd, means there will be a negative sign arises, and a negative sign arises, and so it is so this odd in spin orbit coupling term, there is a small mistake. Basically this will be plus P. I'm sorry, there is a small mistake because this field, when you change the momentum, you get minus sign, and this field with P, plus P over here. Okay, please excuse me for this inadvertent mistake. Okay, so basically this shows that if your crystal lacks a spatial inversion symmetry, then your spin orbit field is odd in K. Okay, so this if you change the momentum, the field changes its direction. And this is the reason why you get the spin orbit, the momentum and spin gets locked. So because of this locking, spin orbit coupling induced spin momentum locking. And that is why whenever a spin of positive, a spin of up off-spin electron interact with the spin-orbit coupling or sees the magnetic field due to spin-orbit coupling that moves in one direction, while the electron with negative spin that moves in the opposite direction. Okay, so this is the mechanism that was taken into account, where here the field, the spin is actually can be converted into the magnetization, which is huge. Okay, so with that the field is very large, and then you observe a large anomalous Hall effect in case of magnetized sample. So this concept was first given by Karplus and Luthinger, but later on there were many confusion with that. So this was not well taken because they have not taken care of the skew scattering and side jump scatterings. So this was not well taken, and this particular mechanism is not. Later on, it was shown that there are some problem with this, some issue with this, and this cannot completely specify the anomalous Hall effect. There are several issues that it could not explain, like suppose you have the anomalous Hall effect later on was observed in antiferromagnets and then various other systems in which this particular magnetization is not applicable. So this particular expression could not explain properly all those mechanisms, those were experimentally. So this was later on modified into Berry phase. I'll come to the Berry phase and explain this mechanism better and the link. So now the question came that can we have, because I showed you the ordinary Hall effect, the Hall effect where it deflects the carriers or the electrons into one direction. Therefore, a charge, there will be a charge current or the voltage developed due to the separation of the charges. So you observe a voltage drop here. Now, when you come to anomalous Hall effect due to magnetization, you find that the charges are separated, but there is accumulation of up spin along one direction and down spin along the other direction. Since there is a net magnetization, so up spin or one kind of spin has more electron density than the other kind of spin. So obviously you develop a Hall voltage in this case also. Spin accumulation is there and Hall voltage is also developed. Now next question is that, can we have a pure spin? That means we will have no net Hall voltage, but there will be spin accumulation. That means we can separate the spin directions, the up spin along one direction, down spin along the other direction, but there will be no charge voltage or there will be no Hall voltage. That means exactly the same number of up spin and down spin at the two boundaries. So we'll exactly get the spins separated along the two boundaries, and because the density of electron will be same in both the cases, so there will be no charge voltage. So this is first theoretically predicted, and later on this was experimentally observed also. I'll tell you the concept of this. The concept is that here there is no net magnetization, but so there is no time reversal symmetry breaking in this case. So in non-ferromagnetic material, we can also have spin separation, and this generates, this is totally a spin orbit coupling effect. So here you need to have high spin orbit coupling to observe spin Hall effect. So the difference between anomalous Hall effect and spin Hall effect is that in one case, in both the cases, you have spin separation, means up spin and down spin are separated at the two boundaries. In one case, the density of a particular spin, like either spin up is greater than spin down or vice versa. So your voltage drop is not zero. Whereas in the other cases, you have equal number of spins at both the boundaries. So net voltage is zero, but you have a spin current over here. And because net voltage is zero, so we cannot measure it electrically like in normal way we measure anomalous Hall effect or Hall effect. We cannot measure spin Hall effect in this way. So electrical detection is different in this system. Then how to measure this? This is basically the experimental observation. It was observed in 2004 by some sort of optical way. So they do measure it by core rotation, and they saw that this kind of rotation for upspin and downspin, they observed this particular current only at the boundaries. Okay. So this is a kind of experimental observation of spin Hall effect. And there are other things like inverse spin Hall effect, or they convert the spin current into charge current by adding some large spinor bit coupled material and all those things. But definitely this gives you that even without a pure or a ferromagnetic material, we can observe the spin Hall effect, and we can separate the spins or the carriers having up and down spin. So the next one, I'll introduce you the quantum Hall effect, which actually revolutionized the concept of Hall effect. The quantum Hall effect was the first experiment was performed by Klitzing. He was basically developed this a MOSFET. He was working on a MOSFET, silicon MOSFET basically, and then tried to measure the Hall effect or try to find out the Hall voltage across a two-dimensional sheet. So he designed it in terms of a MOSFET, and he considered a two-dimensional electron gas over there. So the observation is that he observed that when the magnetic field is high, if we keep on increasing the magnetic field, instead of a straight line that you normally see in your laboratory experiments, you observe steps kind of Hall resistance. So the steps are very, very flat. The surprising part is that you can change the dimension of this measuring two-dimensional system. If you change the dimension, if you change the material, even if you change some sort of disorder also, like there are some defects or disorder, doesn't matter. You exactly get the steps, and the steps are very flat. And what are these steps? These are basically, you get something like 2 pi h squared by e square nu. This rho xy that you see, the rho xy is 2 pi h squared by e square nu. What is this nu? Nu is some sort of integer. And the integer, basically, now if we compare this with our normal classical Hall result that we have obtained P by NE, so if you compare this, basically this, the comparison gives you this number n equals to B by phi naught nu. I'll explain this phi naught later on. This is basically a quantum flux. Okay. And nu is the number of electrons, n is the number of electrons to require to fill the n Landau levels. I'll tell you briefly what this Landau level represent. So now this is integer, and why these plateaus are so flat? Okay, to understand, one more surprising point over here I want to specify is rho xx. I'll show you later on that rho xx should be 0. You can observe it 0 at certain points, whereas at other points you can see spikes in rho x. Okay, and where do we see the spikes? At the point when there is a change in these steps. So all these correlation I'll show you. Now at this point I'll mention why I had told you that the relation of conductivity and resistivity, like conductivity is 1 upon resistivity, that is applicable only in matrix form. I'll show you over here. So this is the relation of conductivity in terms of JEE. So J equals to sigma E or E equals to rho J, in whichever way you take. Accordingly, you can get the relation of rho xx and rho xy sigma xx, sigma xy, rho xx, rho xy. So this is the relation that you get from these two matrices. What you see here, normally, if we get rho xs to be 0, I mean, I'm not talking about superconductors and all. So normally, if rho xs is 0, we say that it's a perfect conductor. But you can see that rho xx equals to sigma xx by rho x square plus sigma xy square. Or in other words, if you take rho xx to be 0 in this particular expression, if rho xx is 0, then what you obtain? Sigma xx you are getting to be 0. So if rho xx is 0 here, sigma xx is not infinity. You don't get very high conductivity in this case. What you obtain, there is a, here you can see, if rho xx is 0, you are not getting sigma xx to be very high or infinite. From this relation, you get sigma xx also to be 0. When sigma xx will not be 0, is that when rho xy should also be 0. So if rho xx and rho xy both are not 0, then your sigma xx will also be 0 if rho xx is 0. So this is a surprising relation that normally you don't think of. So what you see here, your rho xx is 0 and you get the sigma xx will also be 0. Okay, so basically rho xx represents the dissipation and sigma xx is say that there is no charge current along the x direction. Okay. Now with this, I'll tell you very quickly what are we looking for. I mean, how do we understand this quantum Hall effect? We can understand this by simply looking at a two-dimensional electron gas system. So where this, I hope all of you must be familiar with this kind of Hamiltonian, that whenever there is magnetic field, so your momentum gets changed. Basically, the canonical momentum you get as P plus EA. So if we take the Landau gauge, we can substitute this A by XB. I mean, you can of course consider the gauge along the, I mean, the vector potential along the x direction also, or there is also symmetric gauge. So in whichever way you consider, ultimate result will not change. So with a simple consideration, you can say that you can write the Hamiltonian. Then correspondingly, you can take the wave function and apply the method of separation of variables. So then you can solve it, and by solving you can see that along the y direction it is simply your similar to your free electron model, whereas along x direction it is like a harmonic oscillator. So you can little bit modify it and write it in this form. So that way you can show that m omega square by 2 and x square, instead of x square, your x is variable, like your center of the harmonic oscillator is changing. So you have additional KLB square. And this additional term LB is defined as root over of h cut by EB, which is the magnetic length. Anyway, since this is the expression of harmonic oscillator, you can easily express it the energy levels. So you get the Landau levels, and ultimately by using the degeneracy of the Landau levels, you can say that the degeneracy is AP by phi naught. So A is the area and B is the magnetic field. Phi naught, as I have mentioned, 2 pi h cut pi is the quantum flux. Okay. So basically, so you get here the discrete, the energy levels which are very close. Now you get Landau levels in one direction. So these Landau levels are not like these. The Landau levels are actually extended. These are not flat, just lines. You have this kind of localization, and this arises due to disorder, which is very important to obtain the quantum Hall effect. So okay, now with that, if you turn on the electric field, you will see that you can get the I mean, we have again applied the same analogy that we have applied in case of Hall effect. When I explained from the Hamiltonian, you can get the energy term. Then this expression I have already told you. So here you get minus of E by B. Now, this current, I mean, you can get now, you apply the simple equation like mv equals to p plus ea. So from where you can get the current as ep. So ep now taking this particular one, IH cut delta ea. Now again, the vector potential you express in terms of the magnetic field epx with the Landau gauge. So with this simple calculation, you can show that Iy equals to Eb sum over of k E by B. So this sum over of k is actually the number of electrons, and that we express as AB by phi naught. Area is the area, B is the magnetic field, and phi naught is the quantum flux. So now, okay, this we got the expression of n, and this n is correlates with the number of electrons that we take, number of electrons per in each Landau level. Now each Landau level, then once you know the degeneracy, then how many Landau levels are filled, then you can connect that with the Hall conductivity. I'll come to that point. Now the next part is that how do we get the edge current? Okay, so from here you can calculate, because you obtain the current ultimately. So once you obtain the current, you can get the conductivity also. So from here you can show that the conductivity is 0, basically the along x direction or the longitudinal conductivity, whereas the transverse conductivity or the Hall conductivity that you find to be E nu by phi naught. Okay. So this is the same nu that you observe in integer quantum Hall effect. Okay, ultimately you can convert this to your resistivity. So rho xx is 0 and rho xy is minus of 2 pi h cut by E square nu. Now, how do we get this edge current? That is because when you draw these Landau levels, you can see that at the bulk, they are away from the Fermi level, whereas you get this field, this is field up to the Fermi level, and this only at the edges you find these carriers. Okay, and mathematically also you can show this, that at the edges, because along the this direction, along the particular direction, if you take at the edges, there is an additional potential that you can introduce because there is a cut. Okay, so because of this finite geometry, you can have an additional potential, and which by Taylor expansion you can this Vx contribution of this will be 0, but ultimately you will have the contribution del V by del X over here, because when you calculate Vy, the ultimately you will get a term like minus of 1 by Eb del V by del X. So this particular del V by del X term for the left and right direction, this will be either greater than 0 or there is again a mistake, this will be less than 0. I'm sorry. So this By will have different for the left and right, it changes its sign. Now, now we'll try to understand this quantum Hall effect. Basically, you have the in the bulk you have insulating state. So in the insulating state, there is no flow of current. So you have simply cyclotron motion. Now, when you come to the boundary, you have these skipping orbits. That means because of you have applied the magnetic field, and the electrons can move along one direction, as I show you at the edges, your V will have along only in one direction. Okay, so in the other edge you will have the other direction. So in this edge, because they cannot change their direction, so they have to skip the orbit, they cannot complete the orbit, so they have to change the orbit like this. So with this you can see that the edge current develops. Okay, so edge current develops over here. So in the bulk you have insulating state, whereas you have this edge current. Okay, and because of this edge current, you will have a connection between conduction band and valency band. So this is called the edge state. So the edge state develops because of this particular from here in this diagram also you can see the edge states. So at the Fermi level there are edge states, not at the bulk. Okay. Okay, now this is all about, we understand integer Hall effect, but how can we give more physical significance to this n? So what is the significance of this n? Although we express this n is related to your Landau levels, the filling, number of Landau levels, or how many levels are filled and all that. But to give it more physical significance, we'll relate it to the Berry phase, and from where this topological, the concept of topology came into picture. But that let us understand this Berry phase. So this can be understood. I mean, the simplest thing you can see, you can look at the parallel transport. So if you have a vector and if you have a plane like this plane sheet, the vector will you say that it maintains, the vector direction will be maintained on this sheet in the entire path. Okay. So it will not change its direction with respect to the normal to the surface. Okay, if we keep that and try to move over a closed path, then if your surface is a plane surface, it will be maintained 1, 2, 3 everywhere. You can see when you complete its path, the vector has the same direction. Now, instead of that, if you have a curved surface like in B and C, and you consider a closed path, and you try to maintain the vector direction with respect to the normal of the surface, so you will see that when it when it traverses and again reaches 1, its direction has changed. So this is the concept of parallel transport, and this additional, so the change in the direction of that, or it acquires a additional phase. Here it is rotated by an angle, but there can be additional phase. Okay, so this is the concept of Berry phase. I don't have time to go into the detail. I'll very quickly tell you what it means. So if you have a Hamiltonian, and the Hamiltonian depends on various other parameters, say R are the parameters on which the Hamiltonian depends. And if we say that there is in the adiabatic limit, so these parameters vary very slowly with time, then the adiabatic theorem tells you that whatever the eigenstates, the instantaneous eigenstates, you can express those eigenstates will remain as the eigenstates of the Hamiltonian, even if there is a small evolution of the Hamiltonian with respect to time, because R is varying very slowly. So this was shown. I will not go into the detailed calculation. I'll show you from here that the additional page, if you have n as the state function, when this state function, if you calculate the state function after some time t, okay, after some time t, if you calculate, it will acquire a phase, an additional phase. So this additional phase can be expressed like this, and this obtained from your simple this is the simple Hamiltonian. If you can take the time dependent part, time dependent Hamiltonian, and let us say that the R changes very slowly with time, and H is dependent on this R, then ultimately you take the psi t, which this psi t is again, you can construct from the NR. The NR represents the basis function. So these remain the same basis from which we construct our psi t. So now with that, this additional phase can be represented like this. Okay. So from where you get two terms. So this first term is your simple time evolution that you obtained in your normal time dependent when you solve the time dependent Hamiltonian. And this second term represents actually the Berry phase term. So this Berry phase is the additional phase that you obtained when you look at the evolution of a particular state. Okay, and this additional phase is known as the Berry phase, and it is represented like this. So this delta R, this delta R is the gradient of this function. I mean, gradient means this is the this is basically with respect to this with respect to this parameter R, how much this NR is changing over here. So that we have taken as your Berry phase, and this particular del by delta of NR, if we calculate, and then we can express a Berry connection or Berry vector potential. Okay, this Berry vector potential, again by taking the gradient of this Berry or the curl of this Berry vector potential, we can write the Berry curvature. So this Berry curvature is basically the curl of the Berry connection or Berry vector potential, and this we obtain, this Berry vector potential we obtained on a on a chord path like your Brillouin zone. On the Brillouin zone, if your state functions whatever you take, so if there will be any transport on the Brillouin function, then you can see that there will be an additional phase develops. Okay, and you may not get Berry phase in some cases. Okay, but this is the phase that you may obtain if there will be some particular. It depends on the properties of the Brillouin zone. So now the Berry phase you express in terms of this Berry connection, like this gamma n, and Berry curvature we write omega n of R. So if we integrate this Berry curvature over over a closed manifold, you can see that this is 2 pi of n. This n is invariant, or n is the gauge invariant. So later on I will connect this with this. So in solid state physics, basically you can, we don't take individual state. Basically here our states are our block states. Okay. So in terms of block states also, you can define this Berry curvature. Like here our states, I take UMK. Okay. So UMK or UNK. So taking the block states also, the Berry connection and Berry curvature are expressed like this. I'll come to the chart number also in the next slide. So now what is the link? I'm talking about Berry phase, then the Hall effect is different, but Hall effect is not different. So there is some sort of called Kubo formula. Kubo formula, I mean, quantum mechanically you can derive by taking the spectral function. This has been derived from the linear response theory. So they have shown that your sigma x is actually defined like this. And in terms of this is your Berry curvature. So this Berry curvature, like, I mean, you are probably losing the link between them. Let me bring you to the Berry curvature. So the Berry curvature, you can see that it is actually del by del k. Here, the parameter R we have taken as the momentum, and the states are your block states. So the momentum with respect to the change in momentum, how much you see the change over the block states. Okay. Now you can see this is like in 1 dimension, and if we expand this in 2 dimension, you will have the change here. The change is with respect to like del A by del K mu minus of del A by del K nu. So there are two. This mu nu are nothing but XYZ. Okay, so that you can further expand and like in this form. So you can see that here the relation given by sigma xy, you can correlate in the x and y direction. You can see that del by del y of whatever the A in x direction, and del by del phi x of whatever A or the Berry connection in y direction. So this is the link. So basically this represents, the entire thing represents the fxy or the Berry curvature. Okay, so considering the Brillouin zone, or maybe TKNN first time derived or showed you the link of this sigma xy. So they took the Cuba formula and tried to correlate with the Berry curvature. So they saw that if they take the Berry curvature and integrate it over a torus, first they consider the Brillouin zone in form of a torus. Torus because they take the gap to be 1. They keep the gap over there, or the genus to be 1. So if you integrate it over the Brillouin zone, you can see that when you integrate, you will get a number. So basically, over a Brillouin zone, d square k of fxy, this represents the Berry curvature, you get a number, simply a number, an integer, basically. So this integer represents the Chern number, okay? So from here you can show sigma xy is minus of e square by h squared, and c is the Chern number. Okay, so this is the Chern theorem. They say that this is the same thing that I explained. So how do we connect this Chern theorem? You can connect similar to this is a mathematical property, Gauss-Bonnet theorem. So this Gauss-Bonnet theorem, if you on a geometrical curvature, if you take the curvature is like 1 by r1 and r2. So if you take this some sort of curvature and integrate it over a surface, you will get it like 2 pi chi. Chi is 2 into 1 minus of genus. Genus is nothing but the number of holes over here. That represents the number of holes. Like over a sphere, you can do it. Over a sphere, you will get genus to be 0. So here you will get 4 pi. 4 pi as the surface area that you know. And same thing you will get if you take any flat surface. So the important point is over here is that you can distort, okay? The surface you can distort, or you can deform it without closing the gap, okay? Or opening the gap. So if you do that, your integration won't change, or this number doesn't change. But this number will change if you have a different number of holes. Like if you have 0 hole in this case, 1 hole here, 2 holes here, 3 holes here. So the genus will change accordingly. But if you deform like this, you can make a coffee mug, or this you can make a flat surface like a rectangle, or like a plate or anything, the genus will not change. So there is a connection between topology and of topology and this particular symmetry, or you can say that the Hall conductivity. So we can connect this because if you look at the band structure, there is a geometric topology here, genus 0 or 1. And in the band structure, what we relate with this topology is that here, whether there is a gap in the Fermi surface or whether there is any crossing in the Fermi surface. So if we are crossing, there is only one time the crossing is there, then the Chern number will be 1. Or if there is no crossing, there is a gap, it will be 0. Like the Chern number is 0 for a trivial insulator and it is 1 for non-trivial insulator. Okay, so there is a correlation between this the topology in geometric sense and band topology. The next point is that can we achieve the separation of chiral mode, like quantum Hall effect we understood. So this quantum Hall effect, we can see that we have this kind of, we are left with, like, we have the edge states, we could get this kind of behavior by applying very high magnetic field. So here the question comes that can we observe this effect even without the magnetic field? And the answer is yes. This was the answer is yes. The first theoretical prediction is given by Halden in a graphene lattice. I'm sorry, I'm taking too much time. Can I take a little bit?
Madam, yes, you can continue for another 10 to 15 minutes if you want.
Okay.
It is interesting, so we are now also, we can join.
I actually skipped many of the steps. I don't know whether
Uh-huh.
students have really got it or not.
For students, it is little difficult, but we are enjoying.
Okay. I thought of explaining it in more like detail, but with this, I mean, small duration, it is not possible.
And faculties are also there in the participant group, so
Okay,
they
okay,
must be able to follow.
okay, okay. Okay, thank you, madam. This is the first prediction that was given by Halden. So he showed that if you have a periodic magnetic field like Br is not equals to 0, then you can open a gap, okay? And you can have a quantum Hall state in this situation even without magnetic field. So he just calculated from a simple tight binding model and showed that you can have quantum Hall state even without magnetic field. But this was also extended to 3 dimension, I mean other systems and all. But the first experimental observation was done in 2007. And they showed that you can have quantized Hall effect. Okay, you can have quantized Hall effect in this one. And this they observed in a kind of multi-layer system. They keep HGTE, which is having high spin orbit coupling, and they sandwich it between two CDTE layers. When the thickness of this HGTE layer is greater than a particular critical thickness, then you will find this kind of Hall effect. So this Hall effect, why it observed, they calculated the band structure and they saw that there is a band crossing. There is band crossing around the Fermi energy. So this band crossing is linked with the Chern number that I showed you in integer quantum Hall effect. Okay, there is once the okay, you can look at this degeneracy. This degeneracy is coming due to the you must be knowing about the Kramer's theorem, that for any odd number of electrons there is always a degeneracy of the band spin half particles. Okay, so so this corresponds to a quantum Hall state, and is different than the trivial insulating state where you have a gap. So you have a gap in the bulk state. In addition to that, you have some edge states, and that is why you observe this particular quantized Hall resistance even in this system. Okay, so this is further explained. How do we understand this quantum Hall system and quantum spin Hall system? So this basically represents a quantum spin Hall system. Why? Here we observe this without magnetic field. We observe this without magnetic field, and the role of magnetic field is played by the spin orbit coupling here. I showed you the spin orbit coupling can give you an effective magnetic field from the very beginning. So the effective magnetic field that is developed within the material, that plays the role of the magnetic field over here. And you can observe quantum Hall effect. So basically, because of this analogy, we call quantum Hall effect where you get the edge states. So in presence of magnetic field, and there you have insulator and quantum Hall state. This insulator is vacuum. So at the interface, you get these edge states. Whereas in quantum spin Hall effect, you don't need external field. Your internal field plays the role, and because you don't need time reversal symmetry breaking here, so the magnetic field, the role of magnetic field is by the spin orbit coupling, and I have shown you from the term that this can induce spin momentum locking. Spin momentum locking means depending upon the direction of the spin, the velocity can be either either rightward or leftward. So that is shown over here. in quantum Hall state, you have the charge current over here where both the spins are intermixed. So you will only have the charge current here. But in this case, you have the spin current. It can be not only the spin current here. If your up spin will move to right side, your down spin will move through left side. So basically the current gets doubled in this case. Okay, so the left spin is so here both the spins in quantum Hall state, both the spins or both the electrons having up and down spin, they move along one direction. Whereas in quantum spin Hall insulator, your spin up electrons move to right side, whereas spin down electrons move towards the left side. So the current gets doubled here. Okay, now this is a simple analogy. Now the question comes, when you have conventional, you combine conventional insulator with spin Hall insulator. So when there will be a crossing, okay, so you have when you have quantum Hall insulator, you have a different Chern number. When you have trivial insulator, you have another Chern number. So at the edge, when there will be a difference in the Chern number, the transition, it cannot simply transit like this. You have to come across with the conducting edge, and that is the concept of edge states develop over here. So you cannot have you cannot simply a smooth transition from one state with one Chern number and another state with a different Chern number. So this transition occurs via an edge state. So this is the origin of edge state that develop in case of this quantum Hall insulators. Okay, so quantum spin Hall insulators, this is the observation, and this is a schematic again, that spin up electron will move in one direction and spin down in the other direction. Anyway, so basically again all those are similar. So this is just the beginning, and then there are so much developments already done in this field. This is a kind of band structure that you observe here. So this is some realistic band structure. Look at experimentally found, theoretically developed. So a lot of developments have been done in this direction. So I will not go into the detail. So the last thing that I will tell you about the magnetic topological insulator. So what we learned about Hall effect, anomalous Hall effect, quantum Hall effect, quantum spin Hall effect. Then there is only one thing left, which is quantum anomalous Hall effect. So how do we understand quantum anomalous Hall effect? Is that you will have quantized Hall effect, but there will be anomalous. Anomalous means in due to magnetization. So you will have your quantum spin Hall kind of system or quantum Hall kind of system, but with magnetism. So in all those quantum Hall effect and quantum spin Hall effect, you don't need magnetism. But here, when you have quantum anomalous Hall effect, you need a magnetic topological insulator. So basically, we need a magnetic topological insulator where you can see that your rho XX, you only rho XS should be nearly 0 and rho XY should be like h by e square, or rho sigma h, or Hall conductivity should be e square by h. So this was first proposed, and later on it was experimentally observed in several systems. So first observation they got in chromium doped. So bismuth telluride, bismuth selenide are well known topological insulator. And when you dope with some magnetic ion like chromium, then you can see the quantized anomalous Hall effect, where rho xy, I mean, what is the difference between anomalous Hall effect and quantum anomalous Hall effect is that in anomalous Hall effect, you see that the Hall effect is proportional to magnetization. But here, it is not proportional to magnetization. So the steps you get exactly at the point e square by h. Okay, you can see that if you plot it in terms of in the units of h by e square, rho xy, you can see that this is at 1, exactly touching 1, which is like 0.987. But in this case, the rho xx is not exactly 0, it has certain value, and in terms of kilo ohm actually. So later on, very recently, it was shown that if you have a very clean sample, you should have very clean sample without any disorder and all, you can get rho h equivalent to like very, I mean, it's nearly e square by h, whereas rho xs is close to 0. Okay, in this case, you can see that rho xs is close to 0, except the spikes where you see steps in the rho h. Okay, so this rho h is very close to e square by h. It's close to 1 basically. Okay. So there are other topological materials like Dirac semimetal. So these are the different one: Dirac semimetal, Weil semimetal. Even you can have. I will not go into all that. I'll just last thing what I will tell you, that anomalous Hall effect can be observed in antiferromagnets also, because what we saw that the Hall effect that you observe, it is actually related to the Berry curvature. The Berry curve, if there is finite Berry curvature, you can have contribution to additional contribution to Hall effect, and this additional contribution arising from Berry phase is also applicable to the ferromagnets as well as antiferromagnets. Later on, the concept given by Karplus and Luttinger is revised, is modified and expressed in terms of this Berry phase or Berry curvature. Okay, so basically the quantum spin Hall states are also topological states or topological quantum matter. So there are many different types of topological quantum matter. Not only topological insulator, you can have topological Weil semimetals, Dirac semimetal, spin liquids, and many other systems. Even correlated matters. There are many correlated matters. Okay, so maybe that is the topic of another lecture. So finally, you all are aware of the Nobel Prize in 2006 that was given to Thouless, Halden, and Kostrilitz. So the prize is basically for the topological phase transition and topological phases of matter. Okay, I think I'll stop over here. Thank you very much. I am now open to the questions.
Thank you, madam, for such a nice talk, and you explained some of the fascinating phenomena in condensed matter physics in a very lucid way. So now I will just read out some questions which are in our chat box for your response. So the first question is given by Malay Kumar Das. So can we expect anomalous Hall effect in ferrimagnetic system?
Yes, you can observe anomalous Hall effect in ferrimagnetic system also.
Okay, thank you. So another question by Arunima. So how the quantum fluctuations affect the quantum Hall effect?
Basically, quantum Hall effect is very robust, and I have told you, even the dimension or small disorder also doesn't matter. So quantum Hall states are not affected by that.
Okay, thank you.
It's very robust system.
Okay. So another
So
question
you can
by
have disorder. You can have disorder, but
it doesn't matter. Okay. So one more question by Soumyakant Panda. So he has asked, how can we extrapolate the contribution of the anomalous Hall effect from the general Hall effect data, and can it signify the presence of skyrmions on the system?
yeah, first of all, you can separate if you measure the total Hall effect is a combination of your ordinary Hall contribution and your anomalous contribution. So ordinary Hall contribution, we know that it is proportional to the magnetic field B. So if there is any linear term at the high field state when the magnetization gets saturated, so you will have the contribution from the ordinary one. So from the linear region, you can calculate what is the normal Hall conductivity or normal Hall resistance, that you can subtract and get the contribution of anomalous Hall effect. Basically, the normal part or the linear part from the entire Hall contribution, you can subtract.
Okay.
To get the anomalous part.
Okay, the last question from my side. So I want to just ask you why you always talk about this time reversal symmetry when you discuss something about spin orbit coupling or Berry curvature or any such some quantum phenomena in condensed matter system. I mean, what is the significance of this time reversal symmetry? Why you should do? Okay.
Okay. So time reversal symmetry, when we say you have a ferromagnetic system or any magnetically ordered system, so there you break the time reversal symmetry because you break the time reversal symmetry. So anomalous Hall effect, when we say anomalous Hall effect has been observed in a magnetically ordered state. Okay, so there the time reversal symmetry is broken. But when you come to quantum Hall state, so there if you apply the magnetic field, so in presence of magnetic field, the symmetry is broken. But when you come to spin Hall effect or quantum spin Hall effect, the role of the magnetic field is played by spin orbit coupling. So spin orbit coupling is an intrinsic character of the material system. So this is a magnetic field which is developed within the material, not by magnetization or long range ordering or not by external magnetic field. So when you have spin orbit coupling or spin orbit coupling induced effects, so in that case, the time reversal symmetry is not broken. There, the symmetry is preserved. So when you have a quantum spin Hall state, the time reversal symmetry is preserved there. It's not broken.
Okay,
so
thank you, madam.
I just showed you the comparison when you have broken and when you have preserved. And in which case you want this to be broken. Like for anomalous Hall effect, you want this to be broken. Similarly, in quantum anomalous Hall effect also, your symmetry is broken. But not in quantum Hall effect or quantum spin Hall effect or spin Hall effect. In this thing, it is not broken. Oh, sorry, not quantum Hall effect. Quantum Hall effect, you applied a field. So there it is broken, but not in the other case.
Okay. So let us thank once again Professor Mohapatra for her beautiful talk. Thank you once again, madam. Thank you.
Thank you. Thank you.
So finally, we are now at the end of our 5-day series of lecture webinar from tiny atom to solid to cosmos, the quantum aspect. It's my privilege to propose a vote of thanks on this occasion. So there are many people involved in organizing this 5-day event. To begin with, I would like to give a special thanks to Institute of Physics Bhubaneswar and the director of IOP, Professor S.M. Yusuf, for accepting our request to collaborate with us in jointly organizing this webinar. In spite of his busy schedule, Professor Yusuf not only joined us as chief guest for the inaugural function, but also delivered a talk on magnetic material. Thank you very much, sir. We would like to thank Professor Devkan Samuel, coordinator, IOP, for his kind cooperation, suggestions, and providing scientific vision for successful organization of the webinar. Now it is time to thank all the distinguished professors for accepting our request to deliver the talk in the lecture series. Professor Ajit Mohan Srivastava from IOP Bhubaneswar, Professor P.S. Anil Kumar from IIC Bengaluru, Professor Goswami from IIT Kanpur, Professor Samuel from Institute of Physics Bhubaneswar, Professor Swai and Professor Senapati from Niger, Bhubaneswar, Professor Chandana Rath from IIT BHU, and finally Professor Niharika Mohapatra from IIT Bhubaneswar. Indeed, we are very grateful to you all for enlightening us on various research areas of recent advances in physics. You all are the pillar of the success of this webinar. Next, I would like to thank our principal, Professor P.K. Patra sir, for his continuous support and encouragement to organize this webinar. I would also like to thank our TQ3 coordinator, Professor P.K. Parida sir, for his kind support, and Professor A.N. Acharya sir for his valuable inputs, and State Project Administrator SPI, Professor Antarjami Mishra sir, for his encouragement. I would like to thank the heads of various departments and the faculties for their valuable suggestions and guidance in organizing this webinar. I further extend my hearty thanks to all the participants, including students and faculties from CET and other institutes, for joining the webinar, providing feedback, and interacting during each session. This made the webinar a grand success. Finally, a big thank to our head of the department and convener of the webinar, Professor Babita Ojha Madam, for smooth conduction of the webinar. I also thank my colleagues, Pratima Madam, Harapriya Madam, Samita Madam, Priyadarshini Madam, Anita Madam, Sunita Madam, Abhinav Sir, Rakesh Mohan Sir, and staff of the departments for successful organization of this webinar. A special mention, I should thank my dear colleague, Dr. Rakesh Ranjan Sahu, for effectively managing various web-based activities for success of this webinar. Thank you one and all. Have a great day. See you next time. Thank you.